So this is the second part of the example of a bar in a flow, and we're trying to calculate the drag force on the bar using the integral forms of the conservation of mass and conservation of momentum equations.
So this is equation 1, conservation of mass. We're just left with and 2, conservation of momentum. And the surface forces we can split up into the pressure term and the drag force. So the pressure term will be P infinity everywhere, dA over all surfaces. And then the drag force will be minus Fd just in the x direction. So this is the surface integral where the beam crosses the volume boundaries. And that is the two planes that I haven't drawn, right? That's the xy plane parallel to the page. And when the bar crosses that, that's where you pick up that Fd contribution. So for the pressure term, we can apply Gauss's theorem here pretty straightforwardly. Gauss divergence theorem, and we can just say that this is minus integral over the surface area is the divergence of the pressure over the volume, and that is just 0 since P is a constant. So I've copied equation 1 up here, and now let's do this integral piecewise. So what does this mean? It's the dot product between the flow velocity u and the area given by n dA. So what areas are these? Well, it's the inlet area, and now I'm going to sort of show the 3D outline. And the length here is L, length into the page. And then we have the top area. So this is top, this is inlet, this is outlet, and bottom. So we have really 4 areas that we're interested in here. So for equation 1, the first integral is the inlet, and it is rho u infinity times n dA, which in this case is just L dy. Yeah, the length L is constant and u is constant into the page, so it's just L times the integral over dy. And then we have a minus sign for the outlet because the normal points in the opposite direction. It's rho, now it's uy, because our flow field has changed, and it's again L dy. For the top here, our u dot n dA, well, the only component parallel to the surface normal is v, so this really is vl dx. The area is the integral over dx here. So we have plus top, integral over top, rho vl dx, and then minus the bottom, because again the surface normal points in the opposite direction, so we pick up a minus vl dx. Now the v components have opposite signs as well here, this component and that. So these two, even though the surface areas are the same, these two do not cancel. and that's important. Yeah, so we have a net flux out of the bottom and top. So, but the sum of these four components has to be 0. dy really goes from minus h over 2 to h over 2, and rho is constant. The density is constant, right? So we can take that out of the integral, and that cancels everywhere. So therefore we can write this combining the first two integrals. And the L has cancelled here as well because it's a constant. Let me just copy this onto the next page. And then we proceed to our second equation, conservation of momentum. And here we really only have to consider the horizontal component. The inlet now is rho u squared, u infinity squared, L dy, minus the outlet, which is rho u y, u of y squared, L dy, plus contribution through the top, which is rho u infinity vl dx, minus rho u infinity vl dx integrated over the bottom. And that has to be equal to minus fd. So divide by rho l and simplify, and we get plus now the integral here, which is similar to the mass conservation one, just with an extra power of the velocities, u infinity squared minus u of y squared dy equals minus fd divided by rho l. And now if we compare a and b, we can find that this term is the same as that. So you can just substitute that into b and then solve for fd. And what we get is minus fd over rho l is just minus h over 2 to h over 2 uy times u infinity minus uy times dy. So that is our answer here. And you can interpret this a little bit. So you see, as h becomes large, u of y becomes close to u infinity. So the contributions, as you increase your control volume, the contribution of the larger areas becomes less and less, because this term here, the second term in the integrand, goes to 0. And the other interesting thing is that the drag force scales quadratically roughly with uy, with the velocity of the flow field, which also is sort of in line what we know from Newtonian mechanics. The nice thing here is that this whole result is useful for experiments, because you can just need one measurement at the outflow of uy, and if you know u infinity, then you can actually calculate fd, the drag force.